Good morning. I'm Wayne Martin, city engineer. When I studied soil sciences in undergrad, like any other civil engineering major, and I didn't like it. It's too unpredictable. Then I went to night school. I was practicing engineering and law school, that is. And after graduating, I practiced in construction litigation. I did handle some cases involving sinkhole litigation. Lawyers love unpredictability, so then I loved sinkholes. Well, now I'm back with the city, and first thing I noticed was there's about 53 steel plates scattered throughout the city covering road excavation projects that had not been completed. I am happy to report that thanks to the help of Capital Region Water and the City Public Works staff, that number is down to about 20 now, all within a 5-month period. We started to get calls when I started. Well, I'm sure there has always been calls into the city about potholes and road openings and things of that nature, but everything was referred to as a sinkhole. Even a 4-inch pothole was referred to as a sinkhole, which when we hear those words, right, we immediately send people out to determine what's going on out there in the interest of course, public safety. So then you got to think, what is a sinkhole? Let's get a better definition. And the lawyer in me wants the legal definition, and the engineer in me wants the technical definition. And fortunately, in Pennsylvania, we have William Kochanoff, who has a legacy in Pennsylvania of mapping the geology of this underlying karst region, and also in defining in terms we can all understand what is a sinkhole. Without further ado, Mr. William Kochanoff.
I'm going to speak from here. This is all right. Everyone can hear me. I might have my back to you due to logistics here, so I'm not ignoring you. I'm just going to turn my back on you for a little bit. So, we're just going to hop right into this. I managed to thin down my talk from 500 slides to maybe a little over 100. So comb your hair back, and we're going to buzz through this pretty good here. So here we go. So what is a sinkhole? The earliest count I could find was this one back in 1783-84, where this gentleman out in the Lehigh Valley called them landslips. And he says they were tunnel-like hollows, and they were found in the limestone, and they were caused by shifting and sinking of the rock beds at depth. And I thought, well, okay, that's pretty good for that time, describing what he saw at that time. Now geologists, and we have a different way of looking at the way sinkholes are defined, but lately it's become basically to represent basically any hole in the ground that opens up suddenly, or some area that you may notice out in the yard that's, sort of sinking over a period of time. And the idea is to call these things sinkholes when they may not really be true sinkholes. So, basics. In order to have a sinkhole, first you need an opening or a void somewhere in the subsurface. You've got to have to plate the material at the surface. It has to go somewhere. So there has to be an opening underground for it to move into. And then you've got to have some sort of medium to move that material from the surface down into that opening, usually water. So how do holes develop? And I like to think of it as the 3 doors here. And we're going to look what's behind door number 1. And it's a subsidence attributed to subsurface mining. Now when we look at Pennsylvania, we could almost limit this to areas that are underlain by various types of coal, either bituminous coal in the western part of the state or the anthracite region up in the northeastern part of the state. And sure enough, the problems here is that, well, we're taking things out from below the land surface and creating openings there. And what happens is usually that that leaves room for the material overlying it to cascade down into it and propagate up towards the surface. And leaving features that, oh, okay, there are holes in the ground, so it must be a sinkhole. So we have that sort of definition, but more or less we're looking at something that is an activity created by mining. This is pretty common here. Subsidence attributed to past and present infrastructure failures. it's sort of an all-encompassing thing that you got things in the subsurface that have either been left there over time or decomposing, but they're still conveying water in some fashion. So we could think of utility lines, septic tanks, cisterns, water wells, foundations, organic debris that decomposes over time, and then stormwater drains. So, you know, when we start looking at features that we might call sinkholes, they may have a social beginnings to them. This is a cistern up in Center County that collapsed. And those things were usually meant to hold water over time, but over time they've been covered over, and you no longer know that they're there. In a case I was on just last year, a gentleman over in New Cumberland called me up and said, "Hey, I got a hole in the backyard." Here's, you can see the cement patch he put in for the first time, and the second time it opened up. And I'm thinking, well, okay, you're sort of close to where limestones are, but let's take a look. And if you start noticing things, you see a stormwater drain that goes down into the subsurface. It goes down into the ground. And here's a drain right here on the sidewalk here. So, you know, I asked him, well, okay, where do those things drain to? Did they hook up to anything? And the gentleman had no idea where they went or if they were connected to anything. And sure enough, you look down there was a big old cast iron pipe that was no longer connected to things, but water from the house is still going down the drain. It's still draining those areas. And so again, it's something that's still conveying water, even though it's not being used. And of course, over time, cast iron products tend to fail over time, and a lot of times they're under pressure. So when a water line breaks, you've got a high pressure amount of water basically moving material around and resulting in features that, sure enough, they're big holes in the ground, but clearly not related to a natural process, but more of an infrastructure related issue. These are all not in non-limestone areas, which is primarily the focus of this discussion this morning. Here's a good example here of a sinkhole that opened up. Here you can see a pipe that's connected. You got one down in the ditch down here, or in the hole, that apparently has two different kinds of pipes sort of sandwiched together. And then you have one that's really not connected to anything. So this brings, just to focus on that point, that there are things in the subsurface that may be contributing to holes in the ground. Here we have a suspect. See a circular patch, looks bare, there's a little bit of subsidence here in the middle. Ah, that must be a sinkhole. Well, if we pull back a little bit and we look, well, we can see one tree, two tree, three tree. Oh, this is where another tree was located, and we're just looking at where the tree roots have rotted away and it left a void in the subsurface and causing subsidence in that particular area. So even though you have a hole in the ground, there may be numerous causes for why that particular hole may be there. This is not a sinkhole, this is a groundhog burrow. Believe it or not, I get calls for this. You know, there's a hole out in the backyard. Well, geez, you know, there's the material thrown out when the animal was digging. So, and finally, the focus of this is subsidence attributed to karst. And I'm going to clarify that and say in limestone areas and the processes that go along with that. So it all starts with the rocks. This is your geology lesson for today. Basically, if you look at a generalized geologic map of Pennsylvania, we can see it's in nice, pretty colors, and geologists like to use them as to help define what the rock types are within a given area. So that if you were to go in this part of the state and go to different parts and say find the same kind of rocks, you can make connections between here and there. And if there's a valuable resource in that area, by finding it in one area that's labeled as X rock, you can go to another area that has X rock and possibly find that same resource. We're going to strip a lot of that away, and we're going to focus on one type of rock, the limestone, and show you how it's distributed across Pennsylvania. And primarily, you can see it in central and southeastern PA, and a little bit out in the western portions of the state. To focus in on things a little bit, I put the locations of major metropolitan areas within this framework, and you can see that a lot of the major population centers fall within this limestone area in Pennsylvania. Western PA, well, the limestones out there, they're kind of thin. They're kind of separated by other different kinds of rock. And from a sinkhole perspective, they're not really large sinkhole makers. One particular unit, the Vanport limestone, has been mined out in Western PA, has some subsurface mining there, but they're really limited in extent. And there has been some small caves found in there, but no major sinkhole activities. In central and eastern PA, we got real big, thick sections of limestone. Surely this is where things where the majority of sinkholes are occurring. You can see that the rocks have been tortured to some degree. You can see the horizontal layers of rocks have been basically folded in this case, so that there's been some geologic activities here that separate them from limestones out in the west. Southeastern PA, the rocks have been cooked a little bit more, almost to the point of them becoming plastic and being able to deform in that way. Regardless of all that, they're all limestones, and they have a unique property to them, is that they can be dissolved more readily than other types of rock. There you might go out and along through the neighborhoods and see uniquely shaped boulders people will put out as ornamental stones out in front of the yard. And this is where a little bit of chemistry comes into play. And so we have to look at what causes those rocks to achieve those particular shapes. So carbon dioxide, whether it's in the atmosphere or in the soils, mixes with water and forms a weak acid. And it's this weak acid that attacks the limestone bedrock and dissolves it over very, 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 very long periods of time. Some reports saying that the rock dissolves at a rate of perhaps maybe 1 inch of limestone dissolving over 1,000 years. So it takes a really, really long time for the rock to actually dissolve. And surely when we look at limestone, we can almost envision that and look at it and say, yeah, it looks like it's been etched with acids or something like that. And not all limestones are created equal. Some parts dissolve more readily than other parts. And so that relates, and that gives you different patterns. But they also have a common variable in that they have fractures or cracks within the rocks. Now, if we think of our acidic material, our carbonic acid kind of working its way down along these cracks, then over time these cracks can become wider and follow these cracks and create pathways in a horizontal and horizontal direction. And over time, the cracks get wider, and even to a point where we could create underground passages or voids, such as what we see in caves. If we were to strip the soil off of the bedrock in these limestone areas, and you can see the result of this eating away of the rock over long periods of time as it followed the natural cracks in the rock, giving you this hummocky, almost moonscape type of pattern here, called these pinnacles. Again, in certain parts of the state, the rocks have been folded. And like when we get up in the morning, we start bending our arms and legs, we start hearing cracks. Well, it's the same thing with rocks. You start bending them, they crack a little bit more. That allows those acidic waters to move through the rocks along those fractures and to create openings and pathways that may go off into different directions. So it creates sort of something like a plumbing pattern here, where the cracks in the rocks are sort of the pipes, and where the water enters those pipes can sort of be considered as drains. So it's basically a conceptual framework that what gets developed naturally is sort of like a natural plumbing system. But a lot of times these pipes are clogged, and they're clogged with soil. And so, if we were to look at them, here you can see some of these soil-filled cavities that have been formed over the long period of time that are sort of the clogged drains, so to speak. Water, aside from creating the plumbing network, is also the draino, where it also works, in a sense, to flush open the drains. So we can go with our plumbing model and use a bathtub as sort of a way to look at it and consider that. If we consider the bathtub, the limestone, here's our drain, we have soil in it, we add water to it. Well, over a period of time, some of that soil may get flushed down into our drain, leaving a void behind. And it's sort of suspended up in the soil, but as you keep adding water to that system, to that bathtub, that void will start migrating up towards the surface. And at some point, the surface starts to sag, and you might get a depression there, and eventually it can't support itself anymore, and a hole opens up. Sort of like this old abandoned farmhouse, where it took a real long time for the joists and floorboards, everything to deteriorate, causing the roof and building to sag. It took a long time to do that, but the actual collapse of this building may happen very suddenly. So when we look into a sinkhole, we may see what we consider a tunnel. Well, that is sort of like the throat or the opening. This is where all the soil material went down into some other void that's down in the subsurface there. No bedrock here. This is all happening in the soil that's lying above actual bedrock. If we keep adding water to our bathtub model, we can get a connection sometimes from the surface all the way down to our drains. Sort of in this photograph right here, where you can see a stream of water coming down into a limestone drain right here. So keep in mind, it's just a plumbing thing going on here. Water is the key thing to help flushing these drains open. This whole process of dissolving and rocks and soil being moved down into voids and over long periods of time helps to create a unique surface that we call karst topography. And here you can see it kind of looks like a rumpled carpet here. You can see depressions, some sinkholes in here, but it kind of is reflective of what's going on down underneath the land surface. This isn't common to Pennsylvania. I stole a topographic map from Kentucky down near Mammoth Cave area, and you can see that there are certain circular features scattered all over this particular map here. And I colored it in just to show you that these are really the sinkholes there, but they're real easy to see because of the topographic relief. We can go to Pennsylvania and look at our topographic maps and see that, oh geez, you really can't see any type of these sinkholes or anything like that here. Well, sometimes we'll use aerial photography to help identify it and to look at the land surface and see how it's changed over time. And here you can see in a 1958 photograph, not much here, it looks like farmland, but if we look at it from a different time of year, oh my gosh, look at that. It looks like here you can see the location of all of those karst drains, basically where you really couldn't see anything at the land surface. We can zoom in on it, and surely here you can see these are our clogged up drains here. They're holding water. Just like in the bathtub, when you've got that clogged drain, the water sits there for a while, but then after a while it'll eventually drain away. And so we can go down on the land surface, we can see these patterns, we can see these pools of water sitting on the surface, we can see that there's not a lot of topographic relief, there's not a lot of hills, but you can still see it's showing the location of these drains. Even a few days afterwards, once the water is drained away, you'll still see a scar designating the area where that drain was located. So now we start thinking about all that we learned about geology and things like that. We're going to apply it to different things. Well, sure enough, people came over on the boats. They got in the wagons, headed westward, and pretty soon we came to the limestone areas. And sure enough, the area was nice and flat. It was a good place to put roads. They had good soils there for farming, and there were mineral and water resources. So the towns naturally sprang up around there. And sure enough, lands got put up for sale, and communities evolved. Sinkholes started forming, and over time, and this is pretty typical for your standard backyard sink, rather small. But then again, sometimes they can get rather large. Some of the more extreme cases I found along the way, and I'm just going to go through a few of these, down in the borough of Macungie out in Lehigh County. This probably should be I think it's 89 instead of 86 there. But you can see the large hole that formed. It has a nice history to it. There you can see an old photo from the 40s. You see a little pond of water right here. We could go ahead in time to the 50s. Well, that pond of water isn't there anymore. It was a large sink structure. We go into the 60s. Oh, we filled in that hole, planted crops on top of it. Even in the 70s, you could still see a scar showing the area that was once a large hole in the ground. What happened after that, they put a road down the middle, put townhouses, apartments on either side of it. And of course, it took about 25, 30 years to happen, but the hole reopened up, and this is just the process of repair right here. put in a large plug over top of it, filled it in, and here we're talking to a tune of $1989 of $500,000, $500,000 that a small community had to absorb, basically. The corporate plaza building in downtown Allentown, sinkholes opened up in the street, damaged the front end here. You can see where it buckled here and down the back side. Solution, building was so structurally damaged that they had to implode the building. All this to a tune of about a $10 million, this is estimated cost. That doesn't include accessories and all that, but there was a $10 million building. Probably more recently, during the period 1999-2006, town of Stockertown, Tatterby, Northampton County, started out small, started to incorporate and cover other areas. The stream that followed, that sink was right now behind the house in the background there. Moved over, started collapsing nearby roads. Nearby railroad lost its abutment. You can see it fell down into the stream here, large sinkhole in the background. It even compromised the stream to some degree. The Bushkill Creek, you can see sinkhole opened up alongside of it. The creek started to use it, started to migrate across the field, almost to a point where it was going to connect up to another sink and possibly would have hijacked the whole stream and took it across the neighboring field towards a recycling center. That wasn't the end of the story. The road, Route 33, 4-lane, major highway, 20,000 commuters daily, buckled. So it had dropped about 18 inches. Two bridges had to be repaired. We're looking at a general cost of about $30 million estimated cost for repairs in that case. May have heard Palmyra in the news. The borough itself has had a long history of sinkholes. Gentleman here had one open up in his basement. This is Main Street right out behind. These people lost the bottom of their garage. The building, their house, eventually had to get demolished because it was structurally compromised. This is Route 422. They weren't looking for this hole. This was being repaired. There was a small hole off to the right. They found this one. This was about 30 foot in diameter. And all that was holding it up was basically 12 inches of concrete over 422. It's just some over the past couple of years. Members First Credit Union. The Rite Aid is in 2011. And of course we had the Hurricanes Lee and Irene period in September 2011. Here's the Wendy's here at the intersection of Bullfrog Valley Road and 322, right around in that area in Hershey. You can see it was underwater. The road suffered some damages there. In Palmyra, they had a number of holes open up, coincidentally all about the same time. Outside of residence here, a stormwater drain area. All the water for the town went to this one here, which happened to be placed into a sinkhole. The water wants to go into the sinkholes. Let's put a drain in, basically, to help with stormwater drainage. It sort of filled up and caused areas to subside around the actual drain. This is across the street from that particular spot, and the large holes that opened up. Again, all within a short period of time. This one here was a very aesthetic looking one, nice colors to it. It had about a dozen holes open up in a stormwater basin. This is February of this year. Those holes are still there. You go out today, they're still there too. So apparently they were owned by the nearby house who took responsibility for mowing the grass, I suppose. That house has now been torn down and the holes are still there. More recently on Cherry Street, sinkholes opened up beneath these duplexes here. One thing to point out, you can notice the foundation material here, basically field stone. It's not concrete blocks. Where's the footer in this case? So you had the house basically sitting on soil. When the hole opens up, there's nothing there to support it, and it's likely that these houses are irreparable. In the same general area, different times, as that period went on, sinks opened up in other areas. This is the Philadelphia Solutions Materials, I believe, something along those lines. Also in Palmyra, across from 422, this was in February of this year. A large hole opened up and basically the bottom falling out of their tool maintenance shed right there. Utility lines exposed here and over here. And of course, they had problems right out in front of that facility with Route 422, which recently got repaired and just reopened recently. So we can think of things, we see sinkholes, we kind of have an idea now that it's a natural process. It's taken a very, very long period of time to take, and you go through the process here, and keep in mind that process and those processes took a long time, but they were already in place by the time we came along and started building on top of it. So that the plumbing, the drainage, the collapse into other drains, that's been going on for a very, very long period of time prior to any development. We created passages. We could think of it sort of as a plumbing system, and in order to have sinkholes, you need openings in the subsurface, you need something to move it there, and basically there are triggers that help to create those holes in the ground. We can think of patterns in weather going from long and short-term weather extremes, going from drought to high precipitation events. Sometimes those are enough triggers that they can facilitate and create situations where sinkholes can open naturally. And then you have constructional type features, modification of stormwater flows, utility line leakage and failure, over extraction of groundwater, and sometimes poor remediation methods when they fix sinkholes. So when you look at it, sometimes they seem to occur where they've always occurred. And so, by fixing them at one time doesn't necessarily mean that that's the end of it. We can go back and focus now on our towns and townships that are in the general area. We see that all these major metro areas are in carbonate areas. Each one of those, I guarantee, has had some sort of history of sinkhole issues. So we can look at the state again and think of, what is the likelihood of sinkholes opening in cross Pennsylvania. Out in western PA, not so much. If you're in a mining area with regard to coal mining, that's a different case. When we're talking about limestone and sinkholes attributed to limestone, we can look at and consider these two areas, central and southeastern PAs, as having a high to moderate to high chance of sinkhole occurrences. Here's what you can expect. The size of the sinks, they can vary, from what I've seen over 20, 30 years of looking at sinks, relatively small, 1 to 20 feet maybe in diameter, 4 to 10 feet deep. But the point is that the longer they stay open, typically the larger they get. More water comes in, more stuff is getting flushed down into our drains, the larger they will get. Deaths attributed to individuals falling into sinkholes. None recorded in Pennsylvania. This was a staged thing. I didn't actually fall into it, so I'm just using it for effect. Disruption of utilities, loss of water-bearing lines, primarily water and sewer, and you can have compromising of fuel tanks if that's what you're into. This is in Palmyra, one of the basements that is falling out. This fuel tank's kind of suspended halfway over an open hole. There is a risk from gas line explosion, some possible cases in the Lehigh Valley, eastern PA. I put this slide up just as a land use thing. You see fireworks swirled in the background next to the propane tank farm here in the foreground. And of course, there's major to minor damages to structures and property, damage to transportation routes. This is Bullfrog Valley Road out in Hershey during early 1970s. This is Route 283, major highway south of Harrisburg here, going out towards the airport and Lancaster out that way. You can see the sink opening up in the medial strip. You can see our little arch, our little opening showing you where things went. Where did the soil go? And where does it look like it's heading? Just an observation, that you think that perhaps the opening is going beneath this stretch of highway on the westbound side of 283. Rail lines, this is SEPTA line out in Montgomery County. Here's the sink right here. Here's the transportation, the train still going. In case of chemical spills, surface and groundwater can be contaminated very quickly, and it can travel underground in a really quick period of time, or and take days to move through it. This is out in Lehigh County. You've got sinkhole filled up with battery casings here. Out in the country, it's a different story where sinks are often used as waste disposal sites, not just for inorganic things, but organic as well. You see dead animals sometimes within these features, and you know that things that you put into it, knowing what we know, that it's just a plumbing system. We're putting things down the drain. It goes directly to the water table. Someone down the road is probably using this water, and you know, bad things, and we know bad things that can occur and be harbored in groundwater. So it becomes a risk in that respect. And so as a municipal authority, you know, sometimes you may feel overwhelmed that things are coming from you from different directions, when you're thinking of all of these variables that you have to deal with, and not just for one incident, but for the entire community or municipality. Some selected events and their cost, you know, it doesn't receive the same notoriety as perhaps flooding on a major scale, but cumulatively over time, you can see hundreds of thousands, if not millions of dollars spent in sinkhole repairs over given periods of time. This doesn't include the mom and pop sinkholes, the small ones that range anywhere from $1,000 to $5,000. There's a hole in the backyard. Well, we put fill into it, you know, and that's it. You know, ranging, you know, and being relatively a low maintenance type of repair. This was tend to addressed at certain times in the past legislatively. The Sinkhole Damage Assistance Acts went through various reiterations during this time period. Amendment to the insurance company law saying that insurance companies had to cover sinkholes in their homeowners policies. None of these passed. The only one that did pass was the real estate seller disclosure law, and within that there is a section in there that says, are you aware of any sliding, settling, earth movement, upheaval, subsidence, or earth stability problems that have occurred on your property? So the seller has to tell the prospective buyer, yeah, there was a sinkhole out in the backyard. But I've had calls, people saying, I'm not telling anybody there was a sink, I'll never be able to sell my house. So, you know, you have to go with it with open eyes and think about the possibilities of being in the limestone area. For the municipalities, being aware of the geology in your area and establishing safety protocols. What happens when the sinks do occur? For the homeowner, being aware, know the history of a property, pay attention to that disclosure law, and get the sinkhole insurance. It's out there, you can get it. It's a separate rider that you can get for your properties. State agencies, if you suspect that you know, if you're in a coal mine area, you suspect subsidence attributed to that, DEP is the persons you need to go to. There's a mining and reclamation, there's abandoned mines. If you suspect a contaminant entering or being involved with it, there's an emergency response unit set up to do that. With mining, natural aggregates, Pennsylvania's #3 in aggregate production in the state. Sometimes in the processing or obtaining of that material, we have to pump the groundwater out, and that water basically is sometimes used as a support for the land surface. Once you start monkeying around with the levels of groundwater, sometimes that can trigger sinkholes also. And sometimes you'll find a large association of sinkholes in and around active quarries. Other state agencies, like our Bureau, for example, we got interactive maps. Here's our web page. We can tell you, for example, if your house is, if the property's in an area underlain by coal or limestone. We have a sinkhole page online that basically gives you basic information, data that you can use to help in making decisions. This is the Palmyra area, just focusing on it, looking at it, looks like basically a gunshot blast, showing you the locations of those sinkhole-related features. We've gone and taken that data and made it a little more user-friendly, creating density maps, you know, basically red areas bad, green areas a little better. So you don't have to be a geologist to look at it and find out where the action is, basically, with regard to sinkholes. Our interactive map can take you to, you can type in a location, it'll take you down to it and give you information about what particular impact there is on sinkholes in your particular area. And I'm going to end right here, basically, and showing you this is out Huddlestown area. You see a nice property for sale, sinkhole right in front of it. That sinkhole is now filled, but the property is still for sale. So, and this is where I'm going to end up, and basically, you know, entertain questions. We'll hold off till the end of Rich Lee's presentation here that'll follow mine. But the points to keep in mind, it's a natural process. It can be compounded by activities at the surface, related to infrastructure and other things like that. And it's a water-driven system, so when you think of sinks, look for where the water is going, where it's coming from. It can always be a combination of natural related events. The tropical storms Lee and Irene we had got an incredible amount of rain recently. We have those variables to consider, as well as aging infrastructure. You have to consider all of those when we think about sinkholes and where they're occurring. So if we have any questions, we'll hold off till Rich is done with his. Thank you for listening.
Thank you, Mr. Kuchanoff. Our next presenter is Richard Lee, a professional geologist with Quantum Geophysics, a division of Gannett Fleming. He is working on the City of Harrisburg South 14th Street project. I'm convinced that 10 years ago, South 14th Street would have been paved and sinkholes would have continued to develop, and eventually something catastrophic could have happened. Fortunately, with advances in technology, there are means to detect what's going on under there. And the city had taken a step back, knowing, from these maps and things that DCNR has done, that there's, 4 or 5 sinkholes in that region in the past, in as many years. We need to know more. What's going on? And so our next presenter, he's going to tell us some of the techniques involved in studying these for mitigation purposes, for planning purposes, and without further ado, Mr. Richard Lee.
Good morning, everyone. What I'm going to do is follow Bill and sit here and work from the laptop. I only have 17 slides, but let me just what I'm going to do, I'm going to start with a question. What do karst and landmines have in common? Well, the thing they have in common is that they're inherently small and they're unpredictable. So, like those who work with landmines, they use magnetometers or metal detectors to locate and identify landmines. We in our field use geophysical methods to locate these karst features, these voids, pinnacles, fractures, and soil piping. And it's a lot more effective than drilling or doing test pits to find these features. Now, if you were to do a Google search, geophysical methods for evaluating sinkhole activity or karst, my bet is that most of your hits would be one of these 5 methods. And at the top of the list is a method referred to as the multi-channel analysis surface waves, MASW for short, but that's the acronym. And that's really the most reliable method for evaluating karst. And that's the method we used on South 14th Street, and I'll talk about those results shortly. Now, MASW doesn't work everywhere. There are certain conditions where it does not provide very useful information. For example, if there's been grouting in an area and the soils have been stiffened significantly, we do not get very good results. So in those situations, we'll entertain the idea of using microgravity. And microgravity is a method that's based upon Newton's law of gravity. You go back to Physics 101 class. Provides very good spatial resolution, but it doesn't do a very good job determining the depth of the target. So if I see an anomaly that looks like a void, I can't tell the engineer how deep it is, but at least I know where it is spatially, so he or she can drill it to find out how deep it is and how thick it is. Now, the third bullet item is an electrical resistivity method known as 2D ERI, and it's a very popular method with geotechnical engineers. But the thing you have to recognize about this particular method is when you inject electrical current into the earth, you cannot control where it goes. And as we all know, metal attracts electricity. So metal piping will interfere with this particular method. So if you're working in an urbanized environment, i.e. South 14th Street, where you have water lines, sewer lines, storm water lines, this would not be a viable method. You would not get very good results. And the results can be somewhat ambiguous, too, from a car standpoint. An air-filled void and pinnacle both are characterized by high electrical resistivity values. Ground penetrating radar, it's something that's tossed around quite a bit. It's a fancy word, GPR. The fact of the matter is that the depth penetration of GPR is very limited in clayey soils, and in Pennsylvania and most of this country, with the exception of perhaps Florida, when a limestone weathers, it weathers into a very clayey, silty soil. And I think you've seen some of that in Bill's slides. In those types of soils, you get maybe 3-4 feet of penetration depth, and that's it. So it's not going to provide you any information like karst. It should never be considered for karst evaluation in this area. And at the bottom of the list is a method called electromagnetic, or EM for short. This method should never, ever be used for karst evaluation because it doesn't have the sensitivity to pick up small targets. Therefore, it's unreliable. But people use it because these instruments are very easy to operate. And unfortunately, in our industry, anybody can pick up a piece of geophysical equipment and use it. And you can cover a lot of area with this particular instrument, so your cost is going to be a lot less than other methods. So a client who's entertaining a geophysical survey to identify karst, who's unaware of geophysical methods, of course, will look at cost, and someone will come in with very low cost because he's using EM. You'll select that contractor, but you'll get results that are very unreliable. So bear that in mind. If you're in the business or thinking about crafting ordinances with respect to karst, this information should be very useful to you. You don't want to make it a blank a specification and allow people to use whatever they want to use. You want to be very specific about the method, and that way you'll get the results you're looking for. MESW basically provides a continuous profile of the subsurface based upon differences in shear wave velocity, BS. Shear wave velocities are a direct measure of material stiffness. Higher shear wave velocities indicate stiffer materials like rock. Lower shear wave velocities indicate less stiff materials like soil. The nice thing about MESW, it's not impacted by varied piping. It works on paved and unpaved surfaces, even reinforced concrete. It's done miles and miles of PennDOT roads looking for karst. The maximum exploration depth is roughly about 80 feet, plus or minus 80 feet, which is fine for most of this type of work because most of your engineering problems are located within the upper 100 feet. This is a shear wave velocity profile from in Florida, road expansion project in Florida. It basically shows all the elements that you would expect to see in karst terrain. Here we have top of rock, where we have much higher shear wave velocities below it. And within that rock, we have a zone of much lower. Here's a color scale. Cooler colors indicate lower shear wave velocities. Warmer colors indicate higher shear wave velocities, stiffer materials. So within the rock, we have a zone of lower shear wave velocities. This would be indicative of a void or cavity. Note here we have, it's a regular top of rock surface. This is a paleo collapse. What happened is we most likely had a void sitting over here, but through time, as that void and cavity got bigger and bigger, it collapsed and formed this very irregular surface. Not all of the rock collapsed. Some of it's left in place, and this forms a pinnacle. In the overlying soils, we have this green layer, which is much denser sand, sandwiched between two layers of less stiff sand. But the thing to look at is right here. See how this sand is kind of graveling down? This is an indicator of soil graveling, or soil piping. This is an indication of active sink activity. The analogy here would be if you take an hourglass and turn it over, you see that sand just pouring through a small opening. That's what this mimics. This is soil that's being piping down into an opening in the subsurface. We see this. This tells us we have active sinkhole activity occurring. All right, here's an aerial of South 14th Street. This is Magnolia Street up here. This is South 14th Street. And then this is Cloverleaf Terrace down here. Bottom, you'll note 3 lines labeled A, B, and C. The bottom here, A prime, B prime, C prime. This is the end of these lines. These are the 3 lines that we surveyed with MASW. Get on the ground. This is what the MSW equipment looks like. This is a land stream. Basically, this is where our geophones are located all along a Kevlar strip, which has these plates that we screw our geophones onto. And it's tethered to a survey vehicle, in this case a van. And if you look closely, right behind the van, in a 2-inch receiver hitch is our seismic source, which is a peg. And what that does is it slings a rod onto the ground to create a seismic wave. This is our line B along South 14th Street. We're heading towards Terrace, Cloverleaf Terrace. And then for the sidewalks, this will be our line A along this sidewalk, and then our line C will be along this sidewalk. This is our ATV, which we use to drag the land streamer while we're on the sidewalk. And here are the profiles along those 3 lines. Line A prime, starting from Magnolia Street, Cloverleaf Terrace. Here's our B profile, which is within South 14th Street. And then this is our CC prime profile along the sidewalk on the other side. The dashed line indicates the top of rock. Cooler colors indicate the soils. Your depth marks are every every 5 feet. The horizontal scale is marked off at every 50 feet. And the features that pop out at us are these localized areas within the rock of lower shear-wave velocities, which are potential voids. See them also here, as well as on, in fact, all 3 lines, we see them.
What's your depth, Ross?
It varies from 30 to 35 feet down the rock. Note again, as you get deeper into the subsurface, your colors become warmer, higher shear wave velocities, materials, the rock becomes stiffer, more compact rock. We also note that there are lineations within these profiles that we highlight with these dashed lines. These are potential fractures or fracture-like anomalies. And what we do then is we plot these features, these fracture-like anomalies, as well as these potential voids onto a site plan. And then we look to see if we can correlate from anomaly to anomaly, because fractures are linear type features. And when we're able to do that, that identifies the trend and location of a potential fracture. And we've identified a total of 5 potential fractures shown here in brown. 1, 2, 3, 4, and 5. They kind of trend from about 7 o'clock to about 1 o'clock on this map. And on this particular figure, we also plot the location of sinkhole repairs that we know of, you can see in the field. And the magenta colors indicate voids, or sinkholes rather, that we've observed also in the field while we did this work. And there's a very good correlation between what we see in the subsurface and what we observed in the field. So what's happening here is that the sink activity, sinkholes are occurring along South 14th Street, are the result of soil rattling or soil piping into voids or openings into the subsurface. If you take a look at these potential fractures and you extend their trend, that would give you some indication of where other homes or parts of streets may be impacted similarly by sink activity. And surely, a number of these homes have been impacted by sink activity. We have sinkholes opening in their front lawn. Their foundations have shifted. We have very good correlation between what we see in the field and what we see in the subsurface. Now, as I mentioned earlier, MESW doesn't work everywhere, and where it doesn't, we like to use gravity. Back in 2011, a series of sinkholes opened up along Route 422 in Chester and Montgomery County, between just west of King of Prussia. Here we have a sinkhole opening up the right of way. Very large sinkhole opening up in the right of way here. This is the PA Turnpike overpass. This is 422 here. Sinkholes also open up in the median, and they did, PennDOT did some grouting in the median, but also in the roadway, which made it impossible to get very good MESW data. So we did gravity, and if you're interested in knowing what a gravimeter looks like, this is a gravimeter. It's about the size of a George Foreman rotisserie grill. Basically, you sit it on a three-legged template, and you level it, just like a transit. And when it's leveled, these crosshairs will come and meet in the center, and you get a little smiley face that says, okay, you're level, you're ready to go, and you press F5. It says read gravity. Note these keys here, north, south, east, and west. They're there to enter the latitude and longitude for a site that you're working at, because gravity measurements are affected by tides. All right? But the effects of tides are so well known. It's in the software of this machine. So all you have to do is tell the machine the lat and long of your site, and the GMT difference, and it will correct the readings, the tidal effects. And we take those measurements, we contour it after we make adjustments for tides. We also have to correct for changes in elevation. And we create a color contour map of it where the warmer colors indicate higher, stronger gravity readings. Cooler colors indicate lower gravity readings. And what we have here is highlighted with this hatchet mark is a localized area of lower gravity readings. This would indicate potential voids, because voids represent a loss of absence of mass. So your gravitational force would be a lot less. The voids are local features, so they're expressed as localized anomalies in the feature contour map. So we have a feature, this feature here that we've highlighted, as well as up in here. And Geotech came in and they drilled a couple of boreholes, SNK2, SNK5, along this trend to confirm geophysical findings. Geophysics is not there to replace drilling. Geophysics is there to guide drilling. Just like an MRI or a CAT scan is there to guide a surgeon's hand. Okay? Geophysics will never ever replace drilling, but it's there to guide your drilling so you drill smart. You get the most out of your drilling. And what the engineer did here is constructed a profile based upon those boring logs. And here's your top of rock indicated by a dashed line. And then the red indicates voids that were encountered through these borings, along with soil seams. So it's very good collaboration between the drilling and the geophysics. If you look real closely, you'll see this faint gray dashed line and the word fault to the left of it. All right, this is a fault that's identified by the State Geological Survey. And you see no evidence of it where it's plotted, but if you just go to the left of it, along this trend, it's linear trend. That's probably where your fault is. So the lesson learned here is geologic maps are very good for getting you into an area. If you really want to pinpoint something, you really have to get your boots on the ground and do some sort of intrusive work or some geophysics to pinpoint those features. And as Bill mentioned earlier, these fractures and these faults are part of the plumbing that allows water to get into the subsurface to create sinkholes. Once this information is known and it's given to the engineer, he or she uses it to guide remediation. Where do we grout? How much grout can we expect to use in our remediation, as opposed to just drilling here and there and come up with something that in all likelihood would not be very effective. My last slide, geophysical methods can be very effective in evaluating karst conditions. I've proven this numerous times in the past. But the thing to note is that these methods are just tools, just like a scalpel. So in the hands of a good doctor, you get good results. In the hands of a not so good doctor, you may not get very similar results. Similarly, like a backhoe is a tool. You get an experienced backhoe operator, they'll get a very nice clean ditch. If I was to operate that backhoe, it could be a mess. So bear in mind that, again, if you're crafting ordinances, if you're looking to conduct a geophysical investigation, it's not enough just to say you want a geophysical investigation. You want to make sure you get someone involved who's experienced and knows what he or she is doing to get the results that you want. Thank you.
Okay, at this time, we'll entertain questions from the guests for our two geologists or geophysicists. Yes, sir.
In the geophysical methods that you discussed, I noticed you didn't mention seismic refraction or spontaneous potential.
Seismic refraction assumes, this is some assumptions inherent to that method, assumes that velocity is increased with depth. So it's good for mapping top of rock because you're going from the soil to rock with higher velocity. So within that rock, let's say you have an air-filled or soil-filled void. What's the velocity of that material? Much less than the rock, which means if you look at Snell's law of refraction, you're not going to get any refractive events off the top of the void. So you'll never see one.
How about the spontaneous potential? You see the water piping, you see the flow of the ions of water.
SP has been used in that respect in parts of the country. It has been used to some success in the country. I'm aware of it being used in Missouri and the Midwest. But you have to have moving water for that to. You have to have water moving through an area for that to be effective. If the water's just standing still, you're not going to see it. Plus, for SP, you have to have good electrode contact with your force plot electrodes. So to do that, you have to have soil or grass. If you're working on a paved surface or a road, you're not going to have that sort of contact. So it's very limited in that respect, especially in an urbanized environment. And the other thing to remember about SP is moving water is not the only thing that gives an SP response. You could have a corrosion potential, and steel that corrodes will give a potential. Underground fires. I've been able to map underground fires in Valley Forge Park using the SP method because the chemical reaction creates an SP response.
With the combination of microgravity and an SP in a grassed area, an area where you have a fill over a ravine and homes built on it, you can see, you can almost see where the flow is, and it kind of makes sense. And in getting both results of the microgravity and the SP together. We've had some good success. It seemed to make good sense at the time. They correlated like you showed at 14th Street.
Yeah, you can see fracture-like anomalies in your microgravity contour map. And if you overlay your SP data on top of that, you see a linear higher SP response along these fracture anomalies. That would tell you that you have movement of these fractures. Correct.
So this may not be the smartest question I can ask, but I'm curious. So as you are filling in these sinkholes with rock and then soil, isn't as we continue to have flooding, snow melt, some of those things, is that a Band-Aid, or does that actually help to build that land back up? Because it would seem to, I guess, in my very uneducated perspective, that as you continue to have flooding and those types of things, that's just gonna continue to be eroded away. Does that make sense?
I do understand your question.
Okay.
That's a little outside my area of expertise, but it so happens that we have Sarah Fraley here, who is the engineer been working alongside of us, and if you don't mind, I'd like to defer that question to Sarah.
Sure. Thank you.
When sinkholes are filled in, there's a couple of ways, a couple of lines of thought for that. One line of thought is to allow water flow to continue into that area, but to backfill the sinkhole with a graded fill, which helps to prevent the soils, the finer soils, from piping down into the voids in the rock. You would start with a larger size rock and then progressively place smaller size layers of material to create a filter to prevent losses of that soil. Another line of thought there is to identify the actual opening in the rock and to plug that to prevent the movement of material from above entirely into that area, and then to place a less permeable soil above that. Now they have two different uses. If you're plugging it, you're usually in the area of a structure or something directly above it that you want to protect. A graded filter type of backfill is more effective if you're in a general area, because if you plug one opening in the rock, the water still has to go somewhere, and it's possible that a nearby event could be instigated.
Okay, thank you.
Any other questions?
Question for Richard. You talked about the suggestion of an ordinance that, for this type of technical evaluation. With respect to personnel being able to effectively implement that type of program, it seems like the work that you do is highly technical beyond what a normal city civil engineer would have knowledge of. How do cities address that? Do they have advisory committees? Do they have on-call folks that can help with this specialized type of science?
There are townships within Pennsylvania that I'm aware of. Solberry Township is one that I can think of off the top of my head. We've done work out there that have crafted ordinances with respect to cars. And yes, you're right. What we do is much of a specialty. I would tell you to be as specific in crafting your ordinance as you can to optimize payback of results that you're looking for, as opposed to being very vague about what needs to be done. In which case, who knows what you're going to get.
Thank you.
Yes.
Has there been any studies done to see if there's a correlation between
perhaps the bill here.
In general, I mentioned earlier about the rate at which the sinkholes, the limestone can dissolve over time. And it's a very, 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 very slow process. You're mentioning of acid rain. Surely if you put acid on a limestone rock, it's like baking soda and vinegar. You know, they're both going to react and you're going to bubble up and, you know, do their thing. Whether the acid rain contributes directly to more increased dissolving of the rock, that's pretty, no, I can't see how they would do it in the short term. Perhaps in a very long period of time that it may become something. But again, you're talking very, very long periods of time unless you've got concentrated acid pouring into the ground. That's one thing, but just acid rain where you might have a pH of maybe around 4, which is close to what rain is in general for most urbanized areas like that. So yeah, we're effective, but I think it would take a longer period of time to manifest itself in any impact on the limestone.
Okay.
I would like to add one thing real quick. The quality of the rock too. The rock is a contributing factor. Some rocks, limestones, are more susceptible to dissolution than others. And certainly a rock that's been highly fractured will dissolve a little quicker than a rock that's non-fractured. And the analogy here would be a cube of sugar. If you were to crush it and throw it into a glass of water, it would dissolve much quicker than a tapped cube of sugar in the same glass of